Hi. In this video we will finish our little ALU project in Circuitverse. We already have all the relevant components for that. We have this adder with this internal register, this accumulator, and it computes the status flags. We also have these registers, this register bank, and now we have to combine these things. And we also have to define some instruction set and implement it. And I will show you how I did that. And in the homework you can implement a few additional instructions by yourself. But I will also show you why for building a computer and hardware we would have to team up with the engineers. And we should, and I hope that I also might interest you in taking a few classes in the engineering department. This is the demo circuit for my ALU that I will show you in a second, and in particular how I can basically program it with a 16-bit input field. And that the instructions that I implement basically are of two kinds. There are a few instructions for initializing certain registers and some other instructions for doing computations with registers, like adding registers or subtracting registers. You see that we have our 16 registers, the 0 register and 15 general purpose registers. We have the status flags connected to the accumulator of the adder. And then we have here instruction register, which is actually or should be part of the control unit and not part of the ALU. I'll explain you in a second why this in this case is just a simplification. And then we have here this 16 bits, the instruction field, with which I can program this device. Now you see that this instruction field somehow seems to have a structure. I called this bits here op for opcode, and these other bits x, y, and z. So these groups of bits have a name. Now with this opcode I can specify what instruction should be executed in the ALU. And for example, the instruction with code 0000 is initializing the lower 8 bits of a destination register. Now with this 8 bits I can specify a bit pattern, for example this here, which is in hex 1, hex 2, and with that I can identify the destination, for example with that register 1. And now if I hit the clock, you see I have here this bit pattern of register 1. Now the next instruction with opcode 0001 is doing the following. It would left shift this here by 8 to the left and then add the bits here to the lower bits. So let's choose here 3 and 4. And then we have hex 1, hex 2, hex 3, hex 4. The next instruction with code 0010 is adding registers. And with this field I can identify the first register, which should be added to the next register, to register 2 in this case. And here I can specify that the result should be stored in register 3. Okay, kind of boring because here we had a 0. So this is a copy in this case. Let's do some actual addition. Let's store 1 in register 2. Then do again an add of register 1 with register 2 and store the result in register 3. The next operation is for subtracting registers. And here I want to prepare you to the fact that I like the so-called AT&T syntax in assembly programming over the other popular syntax, the Intel syntax. And that means when I do subtraction, I read the subtraction as follows. X gets subtracted from Y and the result stored in Z. So this would now subtract this here from this here and store it here. So we get this. If you actually would like to subtract this here from here, you have to specify register 2 gets subtracted from register 1 and the results stored in register 3, like that. Now back to why this instruction register should actually be part of some external device, not inside of the ALU. With 4 bits I can represent 16 instructions. Now if we would have an actual computer, we also have a memory connected to the CPU with a bus, and then some instructions are meant for the bus and some for the ALU. And also the instructions actually are stored in memory. They first get loaded into the CPU into an instruction register. This instruction register will then be used for decoding. Is this an instruction for the ALU or is it an instruction for the bus? And then the right device gets actually something to do. And in this simple case, all instructions are meant for the ALU, so that's why I just built it into here, so that I have one device. Okay, before I show you how we can set up this ALU and how to specify the instructions, let me also show you some issues why we really need the engineers. Consider this simple logic circuit with 2 NOT gates. Mathematically, how I described it, this is an identity. That means if I change here from 0 to 1, I instantly have here whatever I choose here on the input side. But this is a too simple model for actually describing the reality if you really care about certain details. For example, performance of our algorithm for adding bit patterns. Let me show you in circuitverse a bit better how this actually looks like in reality. I can choose here these flags and connect them with the input side and the output side, and then I can measure how long it actually takes for a 1 to travel from the input side to the output side. Now I use here this time diagram, and now I start the timing. Now you see here 2 lines. Both are currently at 0. This is the line for the input side, this is for the output side. And now if I change here from 0 to 1, you see on the input side it changed to 1, and then it took a while until this could be measured on the output side. So we don't have this in an instant. And that, for example, means that this algorithm that we used for adding bit patterns is not optimal actually. There are better ways. If you know that this is an issue, then you think about what else could we do. So far we thought it's one way. It's computing basically everything or all bits at the same time because we had a too simple model. And another thing, of course, would be could there be problems like that our adder is computing some results, storing it in an accumulator, then we want to compute, then we want to copy the accumulator into the registers, but maybe this result isn't ready yet. We're still doing the computation and already tried to copy whatever the adder did so far into the register. We would have half finished results. That would be terrible. Now, this lecture will not cover all these issues, but in the engineering department, we have lectures that actually do that. In a first step, I will set up a few things so that afterwards I can implement one instruction after the other, after describing the instruction formally first. So that's why I want to talk a bit about this instruction format or how I describe it. I borrowed this notation basically from Donald Knuth. You saw this also in the demo. I do not refer to the bits individually. I refer to them by a name that identifies a group of bits. And these names are op, x, y, z. And each name represents 4 bits. That means later I can, for example, describe with this notation that I want to add 2 registers. And then in this case, x, y, z is used for identifying or for addressing a register. And in another operation, for example, in this operation for initializing the lower half of the register, XY refers to 8 bits. And then you can think of XY as the concatenation of bit patterns, or you just can think about that X and Y are actually not two fields separated. So just ignore this line, this separator. You see, I'm using the state from part 1, from the last video, as a starting point. And the first thing that I now will do is creating some subcircuit for this grouping of the input fields. So I call this op x, y, z. So I first need this 16-bit input field. I will not give it a name, but I will give names to the output fields. I need 4 bits for the op field, for the opcode. And this I also need for X, Y, and Z. And then I also need, actually this should be uppercase. Let's do it nice. And then I also need an 8-bit field for X and Y. Or XY. And now I just use first a splitter for splitting 16 into a group of 4, 8, and 4. And then I already have here the opcode. You can check it here. And this XY will be probably here, this here, and the Z field I also already can connect, as well as the XY field. That's this here. And then I use another splitter for splitting 8 bits into 4 and 4. And that goes here. And this here. You see, this here is changing this bit here and here. That's okay. Okay, and now let's look at the layout. Yeah, looks kind of nice. Save it, and then we can go on. And here I will begin with the input for the instruction and the instruction register. So this here is called instruction. I will also need a clock and an 16-bit register for the instruction. So this is the part that actually should be called control unit. And so you first type in here some instruction, and then it gets copied into the instruction register. Usually this instruction would be somewhere in memory, and then you would copy it into the CPU. Then it gets decoded, which is in this case simple because everything goes, in our case, to the ALU. So this decoding is just this splitters hidden in here. And then of course for debugging purposes it's nice to have here some display so that we can see what is the current opcode X, Y, and Z. And that's a nice thing about Knuth's idea, that you can use single hex digits in this case to represent exactly one field. And that's nice for teaching. That's it. For XYs, we don't need extra displays. So now if somebody types in some instruction with some opcode, then we load it into the register, and then we see this is the instruction that gets carried out in the ALU. Now, what I also will need is an adder. You will see that every instruction in my instruction set can be done with the adder. So I will use this as key component, and this registers, the 0 register and the general purpose registers. And now, in order to make this drawing the wires a bit more convenient, I will also use these tunnels. Let me show you how this works. So this is this symbol here. And then, for example, I can connect, let me change here the direction to right. I, for example, can connect this tunnel, let's say with the op field. Of course, I also have to change this then to 4 bits. Now say I want to have this someplace down here. Then I create a second tunnel. So also should have 4 bits. I think Circuitverse didn't take my bit size. It did. Let's see, sometimes it's still working. Change this to 4 bits. Okay, it was just because it was disconnected. And now you see this bit pattern of the opcode in hex C, in binary 1100. You also can change it to the familiar F. Gets sent via this tunnel device to here. And you also can give each tunnel some individual name. So let's call this tunnel, of course, op instead of T. Then I also should call this here op. And like that, I will connect X, Y, Z, and XY with a tunnel. Okay. Requires some thinking how arrangements can be done nice. Make sure that this XY device has a bit width of 8. All others should have a bit width of 4. Then we also need some simple access to this A, B, and to the choice whether we want to add or subtract something. So we also connect this with some devices, and then here you have to be careful that A and B are 16 bits, each of them, and this adds up is 1 bit. So I call this here A with 16 bits. This here B. And this here A/S, add or subtract. And it should have actually 1. You will also see that this sum that gets computed always can be connected here with the bit pattern for the destination register. So because all operations I will map to a result of adding or subtracting something. But what might be different from instruction to instruction is the ID of the destination register, and of course also what kind of sources, what kind of register do I want to pick up here. So I will also need here 3 tunnels. So this will be 4-bit tunnels. And I need again 3 of them, maybe here And this will be called dest. This one source 0. This here source 1 without a %. And then I also need the picked up values, % source 0 and % source 1. So copy this here, change the bit width now to 16 and direction to right. And this now gets called % source 0. Actually, I want to have this up here so that I can nicely connect later this registers with some output devices for debugging purposes. Okay. There, for the moment, I don't need anymore. Now I also connect already this status bits here. And give them names so that we can use it in a demo circuit later. So don't worry that you see so many red things here. That's because we haven't connected all these tunnels with each other. And also because I have here some name conflicts, but nothing problematic. Okay, and now I also want to connect all these output devices and give them names. Now we actually can do one last thing in the preparation. We have for this register a clock signal. We have a clock signal required by the adder and by the register bank. And actually we can use one clock input signal for that. Whenever something was loaded into the instruction register, we know that it's anyway for the ALU. That means in this case, somehow directly these operands are determined and we directly can compute the result and store it in the accumulator. So we can directly take this clock signal. But at the same time, this clock here, and this one is on 1, should be on 0. So we again do this negation, and you already saw that before. So I connect this here with a NOT gate with the clock signal from before. That means if the rest would work, you would see that now it's computing the result, stores it in the accumulator, and then the result gets copied into the correct register. We now finally can begin with the implementation of our instruction set, and you will see in the end we will have a table where the opcode gives us an index to the row. And that means this first operation with opcode 0 is the first row in this table. And each column of this table will be realized or implemented in Circuitverse with a multiplexer. And as I said before, I now just have to make sure that all operations can be represented as an addition or a subtraction, so that I can do the simplification in my ALU. And so that means I just rewrite it first like that. And then I just have to fill out the blanks. That means I have to specify in this first entry what is the destination register, how to identify it, where I identify it with this bit pattern offset. So that's it. What kind of operation is required? Addition or subtraction? Well, addition. What should this operand A for the adder be? Well, this bit pattern of X, Y but 0 extended. And we have a building block for that, so no big deal. The second operand should be a 0-bit pattern with 16 bits. So we just use the 0 register for that. That means we have to select in the register bank the 0 register with either source 0 or source 1. And I just choose source 0. So I will use 4 bits as input there. And source 1 is actually not needed in this operation, so I can use here any kind of identifier. Now I need first of all a bit or a lot of space. I don't have to see all the things above, I just have to know this table, and I will only use these tunnels for connecting things, for filling out this table. So this, for example, should be the opcode. And you see, if you type in the name correct and then click on it, you see it's changing automatically to 4, because that was how we defined it above. Now this will be connected to a sequence of multiplexers, and each multiplexer is used for one column in the instruction set, and the op field, the opcode, selects the row in this instruction set, in this case the first row. So the control signal size is always 4-bit. Now this is the column for the destination. So I just copy this, change the name to dest all uppercase, and then click on it, change to 4, so properly correct. Direction right. Arrange it nicely, we need lots of space otherwise. And now here I have to select that in the first row, in the first column, this should get this set, this field from the instruction. So this should be set. Okay, name was typed in correct. And then you also should change here the bit size. And then sometimes you have to disconnect and reconnect so that Circuitverse sees that things are correct now. Somehow this didn't work. Change and return. Yeah, you might encounter similar problems, so I will not cut this out. Okay, and now I need this here, or something like this here, 4 more times. So this is supposed to give me actually this A/S, the selection whether we want to add or subtract. So the bit size here should be 1. 1, 1, okay. This time it worked. And then I need a const input. This should be 0. And here we just have const input, so we don't need so much space. Then the next column selects me or gives me this operand A for the adder. So this should be called A, which is a 16-bit input. So we also change this to 16. So this is now 16, this is 16, okay. And here we should get this 0 extended field XY. So I copy this and change it to XY. This should be 8-bit, yeah. And this gives us A. Okay, then here we just have to change the name A to B. The bit sizes then should be already correct. And here I now should use as input percent source 0. That's okay. 16-bit to 16-bit. It's red because source 0 is not defined yet, because I have this source 0 without the percent and this source 1 without percent in the last column, or the last two columns. So this should be source 0 without percent, and this actually should be 4-bit. And if I change it here, it should also change it here. So probably this was incorrect before. But when you have a name, then when you have one name for more than one tunnel, they are basically identical. That's why you really have this tunnel effect. Okay, maybe I need here a bit more space. This here is annoying. So, and this should be 0. The identifier for the 0 register, so 4-bit 0 input. And this also should be 4. Now let's see if this... No, it's okay. Now you see a lot of red is gone. Actually, all of it should be gone because the next thing, this source 1, we don't need actually in this operation. I still fill this out with some arbitrary value, and arbitrary in this case, for example, means the 0-bit pattern. I don't want to have undefined things, although it should not matter whether you actually connect something in this case here. Okay, and this here should be 1. Okay, but now let's save it and test it. At least we don't have anything red anymore. So let's select here, for example, register 1, and I want to store something like that in there. Okay, other register 4, yeah. Okay, for the next instruction, most things now can be reused. Most of all these multiplexers, but also some of the operands. Because for this left shift and then this addition, we again choose the same destination set. We also do an addition, and this bit pattern of A is also the 0 extension of XY. What changed is the bit pattern for B. It should be the register identified by Z, and that means we have to select the register set in the register bank, let's say with source 0, and then that's what we use for B. And again, source 1 can be chosen arbitrarily. Here I filled now the bit pattern of 1. Actually, I wanted to fill it with this bit pattern. So if I would now do this operation, I should get here this here left shifted, then 4 zeros and then 4 ones. So this will be my test case. Now for the implementation, there are only a few things to do. Here I just also connect this here with set. I also connect this here with 0, so this is the same as before. I also use here the 0 extension of x, y. And here I have to do some minor modification. I need this left shifter that we luckily have prepared. And maybe I have to rearrange here a bit things. So this should be here as before. And if we have opcode 1, then we want it through this left shift. Like that. Okay. Then here source 0 should now be selected by the bit pattern of set. So let's put it here, call this set. And actually we are now done, but I don't want this undefined here. And now I can test it. Now again, this should be left shifted, then for zeros and for ones. That's it. So let's fill out the blanks for the next instruction for adding registers. Here we again have this bit pattern set, identifying the destination register. So I already kind of smell opportunity to optimize away one of these multiplexers. We again use an addition, and the bit pattern of A, for example, should be the bit pattern of the register with ID X, and that means the register bank should select this register, and the bit pattern for the other operand would be the bit pattern of the register with ID Y. So we also select this. So let's fill out the table. We have here a set. We have here a 0. Here we need something new. We need source 0 or percent source 0, the bit pattern selected by source 0. Here we need source 1. Here we select the source 0 with X. And here source 1 with Y. And now we test it, of course. So first we initialize some register, 1 for example, with a 1 only bit pattern. And maybe we also shift it. So then I use register 2 with this value. Now I want to see a nice overflow. Come on. I store the result in 2, that should be 0. Okay, now let's do a counter. I'm selecting 1 as input, then I should get here overflow. And now I can count up. Okay. Subtracting registers will be the last instruction where I show you my implementation. And here again, you have to be careful that I'm, for some reason, liking the AT&T syntax in assembly programming, and you have to live with that, with my favors, with my flaws. But still, we just have to fill out the blanks and have to take care of the fact that we are subtracting the first register from the second. So the destination register is again set, so we really could optimize away this multiplexer for this selection. And now a first time is that we are doing a subtraction, so no reason to optimize away this multiplexer. A, that's due to this AT&T thing of me, should be the bit pattern of Y, because our subtractor only can subtract B from A and not A from B. And B should be the bit pattern of X, so that means source 0 should be selecting register Y, and source 1 register X. Okay, so we have here again a set. So you see, we probably really just could have connected these two directly together and optimized away the multiplexer. But optimizations rarely come first. And if they come first, it usually turns out that you were optimizing too aggressive. Here we also need %source1 and here also %source1. But here we have to change this from X to Y. And this from Y to X. Let me first make here the copies. So maybe we also could rethink how we would have done the first operations. We could have swapped that, and then this would be easier now. But again, optimizations are considered not in the beginning, unless it's very obvious. Probably for some people that would be obvious, but this still should work. And that's usually always a good thing for the first approach. Now I already have the values. No, I lost them after saving. So I store a 1 in register 1, and then I want to subtract register 1 from register 2 and store the result in register 2. Then I should get here just 1 bit pattern, and now I'm counting down. I'm sure you know how to fill out the blanks for the last two instructions, and in class we then can discuss about different things. For example, could we optimize this instruction set by just renaming certain things or regrouping things so that the implementation would be a bit easier, and what other instructions would be useful.